Welcome back. We are almost complete with the discussion of the block diagram representation of the FOC algorithm. We have successfully transformed the controlled direct and quadrature voltage references to the stationary XY coordinate system. Now, we shall further describe these physical quantities in the free-phase coordinate system using the inverse Clarke-transformation method. In this video, we are going to dive into the details of the mathematical representation regarding the XY to ABC coordinate system transformation. Let's move forward. Let's have a look to the inverse Clarke transformation matrix. The first question is, how can we deduct the inverse representation of this coordinate system transformation from the previously learned forward Clarke equation? The answer is basically the same as in case of the inverse Clarke transformation. We shall take the transpose of the forward Clarke matrix and then we shall receive the inverse version of it. The zero-order component has no impact to this mathematical operation when we are dealing with symmetrical systems such as a PMSM motor and their control algorithm. So this matrix equation can be further simplified that we are going to investigate in the next slide. I find it important to emphasize that the calculated A, B, and C phase voltages are the reference signals for the upcoming SVPWM algorithm. The latter mentioned logic is responsible for realizing the demanded phase voltages on the motor terminals with respect to the best utilization of the available DC link voltage. On the picture, you can see the two-phase XY and three-phase ABC coordinate systems. As we have discussed before, the real axis of the XY coordinate system aligns with the A-axis of the three-phase plane. By now, we know how to describe any kind of vector in these reference systems, as well as we are also able to transform the vector representation between the two. Here, the U_S vector represents the stator voltage vector of the PMSM machine that we would like to realize on its windings. In the next slide, I am going to represent the scalar equation related to the inverse Clarke transformation, which mathematical operation can be programmed with ease in any programming language. By utilizing the so-called row-column multiplication technique, in case of the inverse Clarke matrix equation, we shall receive the scalar voltage equations for the appropriate phases. As you can see, no zero-order voltage component is present in the mathematical representations, so basically the previous matrix equation is simplified that way. A picturesque way to imagine how the stator voltage vector can be described in the three-phase system is to take the projection of the latter mentioned vector to each phase directions. You may notice that the x and a axes are aligned with one another, so the U_x and U_a voltages shall be equal with one another. The same interpretation can be used for the b and c axis as well, where the only difference is that the imaginary components will be present alongside with the real ones as well. So, to summarize up the inverse Clarke transformation, we have successfully described the controlled direct and quadrature voltages with the help of the current controllers in the appropriate directions. Later, by utilizing the angle information of the rotor pole flux, we described the voltage components in the XY stationary frame as well. In this video, we have deducted the scalar mathematical equations for the transformation between the XY and ABC coordinate systems. The only remaining step to be taken is to investigate how these referenced three-phase voltages can be realized with PWM technique by using a voltage inverter. In the next videos, I will try to explain these more or less hardware-related topics for you. Take care, and I will see you soon.